Hello and welcome. This is a AS AQA Unit 2 video. Now, I've done all of the topic videos, but this one, although I have listed it in the topic videos, it's just one of those things that's kind of a bit of a weird video in terms of the fact that it's not directly a whole new topic in itself. Okay, it's just a video that just explains one or two things, okay, that obviously is quite a common feature of the way they manipulate a topic in an exam. And in this video, as obviously you've known by the title, this is about Newton's second law, and obviously in particular I'm applying F equals ma to an object approaching terminal velocity. Now, it seems to me, through past papers, that quite a common area of testing in F equals ma, apart from obviously you've got your lift problems, your rocket problems, your horizontal inclined plane problems, but this one I personally think is a little bit, they quite like to turn into a 6 marker. So a potential 6 marker on this topic could be obviously state how using Newton's, or it might even just say using one of Newton's laws of motion, explain how the resultant force on an object varies up until its terminal velocity, or something like that. Okay, so it's a potential sort of question. And obviously what you would generally have is this object being at rest or being released from rest. Okay, so in other words, you can, I'm going to almost split this up into like kind of 3 stages here. So the first stage, okay, so we've got the object at rest, it's just falling, okay, it's just literally been released, okay, so the weight is humongous, it's in comparison, okay, the weight is very big, okay, but the air resistance, you can barely see it, okay, because it's not moving, so there's barely any air resistance there, so I'll call this AR for short, okay, so that's kind of the first stage of this. And what you would say if you were labelling this, so what I'm going to do is write the 3 stages, okay, in terms of the diagrams, and then I'm going to write what you would write in bullet points for potential answer. Okay, so as I said, the first stage is about whether weight is a lot greater than the air resistance. This is the first point you make. So you say initially there is little or no air resistance at all. And then you would obviously go on to say, but the weight is acting downwards, okay, which obviously we can link on in a minute. So the weight is acting down. And obviously we're assuming there's no force acting either side, so the forces that way, left and right, cancel out, so you just kind of ignore them really, because there's no forces there. Okay, so that's the first point you would make. But still on this stage, we'd say, well, if you've got to apply it to Newton's second law of F equals ma, you would, well, F is a resultant force, and the resultant force is one force take another, so it's this weight minus the air resistance, okay? So we've got the weight minus the air resistance is equal to the resultant force, okay? So because the resultant force is equal to mass times acceleration, where obviously the mass is constant, okay, the only thing the force can affect is therefore the acceleration. So because the resultant force is the difference between these two, it's greatest, and it will be apparent, it's greatest when it's just released, because there's barely any air resistance, but the weight doesn't change. It's not greatest at the end, it's not greatest during the middle, it's greatest, it's the maximum value all the time. Okay? Excuse me. So, therefore, because... sorry, I was said your word, the next point. You go, yeah, because the resultant force, I'll just label it as F, is equal to the weight, take the air resistance, okay, that's the resultant force, which is therefore equal to the mass times acceleration, where m is a constant. I mean, this little bit is just really, it said you could label it, word it in different ways, but the whole point of this next bullet point, because obviously you don't have to write essays for 6 markers, you can just do it in bullet points, and that's what I prefer to do. Okay, so your second point would be saying, well, because there's the resultant force is the difference between the weight and the air resistance, therefore because it's so big and the resultant force depends on the acceleration because m is constant, as we've said, okay, therefore there will be a huge, therefore the acceleration will be enormous, okay? So the acceleration will be greatest at this initial bit. Now, if you were to draw some kind of graph for this situation, it might look something like this, okay? Just getting you the idea, okay? And then when we get up to a certain, then the second stage is where the, actually, kind of is it split into a second stage? Kind of, depends, okay? So there's this block again, got a mass. The weight stays exactly the same. I'll try and draw the same kind of crappy arrow. Okay, so the weight stays round about, it stays the same, okay? Obviously, the air resistance begins to increase. And then this lends itself to the third stage, really, where obviously you've got the air resistance, and the weight, where they become equal. I mean, it's my crap drawing. Okay, so at the third stage, okay, the weight becomes equal to the air resistance, because obviously the air resistance builds up with speed, okay, so therefore, that's your first 2 points, and then the third point would be actually building up to this, okay, so saying as the object accelerates, so as the object's velocity increases, and obviously you'd have to relate it to what other object it's asking you to work out it for. Okay, so as the object's speed increases, or velocity, so does the air resistance. I just put so does the AR, the air resistance. Okay, and that's kind of the third point you need to make, which is kind of illustrating this diagram here. Okay, and then you say your next point would be, there comes a point when the air resistance, there comes a point where the weight is equal to the air resistance, okay? And if the weight's equal to the air resistance, in other words, the downward force is equal to the upward force, okay, because the air resistance, we can assume it to be, obviously, in the opposite direction to motion, as this is falling, obviously the air resistance will be acting up, okay? So there comes a point where the weight is equal to the air resistance, so therefore the resultant force is weight take air resistance, okay? So and then you would say as the resultant force is equal to the weight minus the air resistance, okay? Therefore, because the weight is equal to the air resistance, there is no resultant force. And as we said, the resultant force is dependent on the acceleration, okay? So therefore, ma equals 0, so therefore a is equal to 0. There's no acceleration at the point where the weight is equal to the air resistance, therefore this object is said to have reached terminal velocity. Okay, so that's a very, very quick kind of recap on that little bit. And as I said, they like to ask that as a 6-mark question. Okay, so all you need to do really is talk about how the weight and the air resistance, their relationship as the object builds speed, and you need to relate the fact that the resultant force is the weight take the air resistance. And the main things with this is the resultant force is greatest at the start, okay, and then it slowly reduces as the air resistance gets larger as the object increases its velocity, okay, and then it comes to a point when the weight is equal to the air resistance, so therefore between the weight take the air resistance is equal to the resultant force, so there's no resultant force, and as we said, the resultant force is equal to the mass times acceleration, where the mass is a constant, so therefore as there is no resultant force, there is no acceleration. So if there's no acceleration, the object remains at a constant velocity. Okay, so therefore it does not accelerate. Therefore, it's reached a terminal velocity. Okay. Now they may the one other variation of this, they might do it as reaching a terminal velocity in air and then it being hitting a liquid after it reaches terminal velocity. And obviously you've got to apply the same principles, except you've got to do it twice. So if this is just describing the first part, okay, if it just says how does it the object reach terminal velocity according to Newton's second law in air, that's what you do. But then if it said well, the ball there then hits a liquid, okay, and obviously because the liquid is going to also, there's going to be the air resistance, or if there's not any this resistance force, I've labelled it as air resistance because that's the resistance in air. But if it's in a liquid, then obviously it's not the air resistance, it's going to be the liquid resistance, which might be a bit higher. Obviously that depends on the viscosity of it, which the viscosity, and I'm not a chemistry student, so I'll give you the basic definition. It just means how easily the liquid is to flow. Okay, now also it's not a proper chemistry definition, but as I said, obviously the way you're trying to get across there is much more, it's got a great resistance, much more resistance. It's got a greater resistance than air. Okay, so obviously the terminal velocity in the liquid will be lower. So that's that graph I was showing you before, and I can't remember what paper it's off. I think it's June 09. Okay, where you've got a graph, and it's kind of explaining this. What we've got here is, you know, you've got your standard velocity, and then you've got time. Okay, and obviously this object is dropped from air. Okay, which is terminal velocity. Okay, so sorry, it doesn't reach terminal velocity, so it increases because the acceleration is acceleration due to gravity. Okay, and then obviously it hits the liquid at this point, which is in the exams labelled as T0. Okay, and then when this, because obviously the gradient of the velocity time graph is acceleration, so when this is flat, okay, it's reached terminal velocity, and that's because quite clearly the terminal velocity in the liquid is going to be a lot less than terminal velocity in air, which might be somewhere around here if we followed it on. Okay, so really that's kind of it for this little side video. Okay, so as I said, hopefully it's been helpful, but as I said, I didn't really want to delve too much into it because it's not that really challenging. It's just basing what you already know, and it's kind of manipulating to a possible question. But I think I'll still put this in the AS playlist. Okay, so thanks for watching. I'm sorry it's not been the most informative video, but if you want a more descriptive analysis of the resultant force equal to mass times acceleration and the variations that has on rockets, lift problems, and yeah, this terminal velocity, I think I do go over it again, but this is just in a greater detail, really. Okay, so thanks for watching. Hopefully it's been helpful, and we'll see you in the next video.